noble cause, I can say, to celebrate the India's glorious 75 years of independence. Friends, as you know, ICAR has taken up many activities, and this is one of the very important activity which has been taken to have the 75 lectures before 15th August 2022. In that series, we have taken many lectures. Many important personalities, they have shared this platform to express their views. You can see that the lectures which we have covered, 68 lectures we have covered till date. We have covered the topics on agricultural research, animal science, fisheries, the policies by Niti Aayog. We can see the lectures on the health, the lectures on motivation, yoga, and many more topics. In the same series, today we are going to have 69th lecture on a very important topic, and that is capacity building and technology development by technical institutions in National Clean Air Program. Friends, this lecture is being given again by a very important personality, a very well-known researcher, Professor Sachidanand Tripathi. Professor Tripathi, he is a professor at the Department of Civil Engineering, IIT Kanpur, and he has won many prestigious awards. To name a few, I can say one of the most prestigious award, Shanti Swarup Bhatnagar in Earth, Atmosphere and Planetary Sciences, J.C. Bose National Fellowship, Distinguished Alumnus Award of Banaras Hindu University, and UP Ratna by Government of Uttar Pradesh. Congratulations, Professor Tripathi, for such prestigious awards, which are to your credit. He is also the elected fellow of Indian National Science Academy, and Indian National Academy of Engineering, National Academy of Sciences of India, very prestigious academies. Really, we are proud of your achievements. He has, I think, he has been the guide for the 15 PhD students and 37 MTech students. And he has, to his credit, 192 plus research articles in international journals, which have a total citation of more than 7,365. Excellent. 4 book chapters. Professor Tripathi has made impactful contributions to address challenges of air pollution and climate change. He has built groundbreaking innovation approaches for indigenously built low-cost sensor-based network technologies for nationwide urban quality monitoring and real-time source apportionment. His work on Taj Mahal discoloration led to policy interventions in Agra city, a very important intervention he made. His pioneering work in aerosol-induced cloud invigoration effect and synergy of coupling between urban land use, land cover, and cloud condensation, nuclei-induced AIV has contributed significantly in future urban planning to avoid flash floods. He is also the coordinator of the National Knowledge Network formed under the National Clean Air Program and an expert member of steering committee and monitoring committees, National Clean Air Program, and member of Executive Council Climate Change Program, Department of Science and Technology. What a wonderful CV your contribution is. So we are thankful once again, Professor Tripathi, to you for accepting our invitation. And I know it's a very early morning in Germany. You are connecting from Germany. And it's a very taxing that you have agreed to spare time despite your busy schedule, research schedule, and sparing time early morning. I think it's that shows a great dedication, a great commitment, and I'm sure your talk is going to be immensely benefiting our students, teachers, vice chancellors, our senior officers, and many more who are seeing either through this Zoom meeting or through the live streaming, which is being done through the ICAR official YouTube channel. So thank you once again, Professor Tripathi, and the floor is yours now. Thank you.
First, thank you, Dr. Agrawal, for being very generous while introducing me. I thank you. I thanks ICAR for giving me this opportunity. I feel very privileged and humbled to be part of such a distinguished lecture series, which is being organized as part of India's 75th independence year celebrations. So I'm very happy, delighted while giving this lecture, and I hope by end of this lecture I would be able to share some interesting ideas which will find some resonance with the ICAR community. For example, something related to agriculture residue burning, what we have found in Delhi, or a new air quality network across the states of Uttar Pradesh and Bihar, which would cover the entire rural landscape of these two large states. I'm sure we'll have something interesting to further, find common ground and for some common collaboration. So with that, I again thank you all, and I would like to share my slides, and we'll begin from there. I hope you can all see my slides well. Dr. Agrawal, can you please confirm?
Yes, please.
Okay. So mainly I'm going to discuss to start with the National Clean Air Program. And then I would also discuss that what kind of structured mechanism we have proposed to Government of India, which I'm very delighted that they agreed upon, which is called a knowledge network. And what is this knowledge network? And as a part of knowledge network, what kind of new science questions we are addressing related to air pollution, which is a emerging global environmental threat, and also has some very strong climate connections. And then would also try to give some ideas, some new emerging ways to either tackle this problem or measure and monitor it. So as we know that you can only manage something if you can measure it. It's a very famous quote by a very top industrialist in US. So that is why we believe that measurements are very important. But how can you measure at scale? That is what is going to be a final theme of my talk. So let me just begin with by acknowledging some of the central funding agencies, being Department of Science and Technology, Ministry of Environment and Forest Change, and Ministry of Environment, Forest Change and Climate Change, Department of Biotechnology or Central Pollution Control Board have been very generous in funding some of our endeavors, efforts. And recently, we have been quite fortunate to receive funds from some large international philanthropies, be it Bloomberg, Ericsson, or Open Philanthropies, etc. Currently, as it was mentioned by Dr. B.N. Tripathi Bhai Sahab, is that I am currently a fellow here at Institute for Advanced Sustainability Studies. I'm a senior fellow here at Potsdam. And I also would like to put on record all the work which I'm showing has been a result of collaborations with my collaborators in India, abroad, and also many postdocs, a whole generation of postdocs, PhDs, and masters have contributed to this work. So mainly the talk is organized in the following fashion. I will briefly tell about National Clean Air Program, and then would quickly switch to the National Knowledge Network, which is a rainbow alliance of India's top technical institutions, IITs and IITs, top universities, and national laboratories, which is a very much pan-national alliance, which currently has a presence in every state and everywhere. Second part of the talk is going to focus on what are the sources which contribute to the ambient particulate matter and ambient harmful gases, which are potentially harmful for human health. How do you improve this technology? So I will show you that how gradually we are doing some indigenous development to improve this technology and make it more affordable, more scalable. And final part of the talk is to basically discuss about these sensors, that these low-cost sensor-based monitoring, and also how to impart more capacity where there is some lack of capacity. And in general, given the scale and the magnitude of this problem, which is huge, you will realize that we have less capacity and we also need to invest in that. So what kind of work knowledge network is doing in that direction, I also will be discussing that. So let me just begin with, this is a very primer slide because I know some of you have some probably prior knowledge about particulate matter, which some of the time we also call it aerosols. So these can be loosely be, used synonymously. So what you see here on the x-axis, you have three different distinct kind of settings. You have anthropogenic sources, which are right here. On the very left on the x-axis, which are basically city. Then you have rural sources where you go for like crop, agriculture, field. And finally, you have deep forest, what we call as biogenic sources. And on the y-axis, again, you see the scale is divided into three regimes. One is emissions, that when these things are directly emitted. Second, in the atmosphere, actually atmosphere work as a chemical reactor. It's a very complex kind of a reactor where all type of chemical reactions happen, which you can think of. And finally, what kind of climate implications these particulate matter or gases can have. So you see, as the particles or the gases are emitted from three distinct kind of sources, then they actually undergo a variety of very complex chemical and physical processes, which convert them eventually to the particles which we breathe or the particles on which cloud drops form. Okay. So these particles, what we breathe, actually are harmful to human health. That's one very important implication. And by acting as a seed to cloud particles, they can also modulate cloud formation, which has all of us know that has very important implications to hydrological cycle, monsoon, and also global energy balance. That is what is shown on the top left. And these particles can also interact with solar radiation directly or even indirectly, which I just spoke before. And by doing so, they can also alter the global energy balance, which has important implications to the climate change. So what you see that what you emit and what happens in the atmosphere, eventually it has strong linkages with human health and climate change, both at local to regional to global scales. So this is a very interesting work was done by actually a German group looking at the adverse health impacts globally due to particulate matter, mainly due to particulate matter. And what you see, there are two plots here. On the left, what is shown is the overall mortality, human health attributed to outdoor air pollution. And what you clearly see in this slide on the left is that India and China actually stood prominently in the dark colors. That means the largest particulate matter induced mortality happens in these two countries. And in fact, there are now emerging estimates that about 1.5 to 2 million deaths per year might be happening in India, primarily due to air pollution. And these are estimates basically made by many top journals, including Lancet. And on the right, what is shown is the sources which you could attribute to the majority of the deaths which is happening because of this particulate matter. And what you see, India is shown as blue, and because of residual cooking. So the sources or the solid wood or even sometime coal, the things which are used are attributed for these most of the deaths which are happening. So basically what you cook inside is not confined. It, of course, it's very harmful to the immediate cooking people, the person who's cooking, but then it also travels outside and then it has a plethora of adverse impacts. So looks like that this slide is not appearing. Oh, some slides are actually looking like that has some problem here. I hope that in subsequent slides are good because I'm directly sharing because of the slides are large. So anyway, I will just go on like this. So this slide actually was on National Clean Air Program, and it has mainly three parts to it. One is that how this program came about. So before National Clean Air Program was launched in 2019, the problem of air pollution was dealt with in a very fragmented fashion. So whenever there is a problem in Delhi NCR, we'll try to deal with that. Or most of the country basically were not part of any comprehensive program to deal with this issue. So first time the Clean Air Program was launched in 2019 on the basis of the measurements what the country had related to particulate matter 10. Particulate matter 10 is basically PM, these particles which you find in the atmosphere. Sometimes loosely we call it dust particles, having size less than 10 micron. So most of the measurement or widespread measurements were available only for particles less than 10 micron at that time. And those were manual measurement. And they formed the basis to basically create this program. And the program has the major target. The primary target is to reduce particulate matter 2.5. So PM10 measurement was available, but particulate matter 2.5 is more harmful to the human health because these particles are tiny, 1,000th in size of human hair. So they can when you inhale, can go into your lung and then can seep through your bloods into organs. So that's why our target in this program is to reduce particulate matter 2.5 by 1/3 by the end of 2024, which has been slightly amended to make it 2025. And there are 3 goals which, while we try to go on this journey of NCAP, there are 3 goals. One is to basically increase the research and science so that we address it more on a scientific basis. Second is to create more institutions and capacity building. For example, what you have seen now in Delhi to deal with this perennial problem of critical air pollution episodes in Delhi, Parliament enacted to bring a new commission. So earlier there was no commission in Delhi. So these kind of new institutions are also very well aligned with the philosophy of National Clean Air Program. And finally, you also want to mitigate the sources. So there are 5-6 major economic sectors, for example, industries or vehicular pollution or agriculture biomass burning or from power generation, just to name you 3-4 very major, or maybe waste and the dust. So these are 4-5 major sectors from where generally the particulate matter or harmful gases are generated, where you try to either replace it by cleaner energy sources, or you try to reduce the intensity of emissions. So this slide, unfortunately, is not at all shown, but because I think I'm just sharing it directly from the Chrome. So it looks like the slide conversion did not work very well. But this slide mainly showed that how the program will be delivered based on the 3 major pillars. So that is all what I just spoke in the previous slide. So we haven't missed too much here. And I mentioned that when the program was on track, then we realized that there is a great need to create capacity because the program is very science driven. The problem of dirty air or the goal of achieving clean air has to be based on hard science. And then you can translate it into better and technologies which can work as per the local needs. You need to bring technical institutions together. You need to bring national laboratories together. And then wherever there is lack of capacity, we also need to impart capacity. So with this idea, we approach the ministry where, as I was mentioned, I'm part of the Clean Air Program. And ministry found this idea very acceptable. And therefore, this is just to give you the timeline of this knowledge network. This knowledge network is a part of National Clean Air Program, which is headquartered, its secretariat is actually located at IIT Kanpur. And currently, if you look on the map of India, it is spread across all states where the polluted cities are there. So what are the polluted cities, which are shown here by this open circle? These are called non-attainment cities. Non-attainment cities mean that the cities where the air is not meeting the standard set by Government of India. So we have National Air Quality Standard, and based on substantial measurement, if air is not meeting those, then we designate them as status of non-attainment cities. So as of now, this program is very city-centric, and under is ambit 133. 133 cities are basically where the Clean Air program is being implemented. And what you see by star, we show these institutes of repute, which have been designated this status for the purpose of contributing to the capacity building under this Clean Air program. So mainly we have all the IITs here, all NITs, all top universities who have a well-established program either in environmental engineering, or sometimes they have some program in air pollution, or they have a established research program, either academic or research program. They have been brought into that. So altogether, there are about 90 plus institutions are part of this network. And the idea is that in every city or in the vicinity of, in the neighborhood of the city, we have one institute which can work with the city authorities to contribute towards understanding and implementation of this program by either generating data or analyzing data, or even helping them through technological development. That's the idea here. So now I will just take you through some of the work which we have done to understand this complex nature of sources which are responsible for the particulate matter and the harmful gases, which are called here volatile organic gases, and some of them can transform in the atmosphere to form particulate matter. So it's very important before we go after them, we plug them or mitigate these sources. It's very important to get a very precise information about which they are and where are they located. So this is a very simple slide to show you that what is the existing practice of doing the source apportionment, which we call understanding sources, are called also source apportionment, right? So the existing practice is basically what you do is you collect particulate matter on filters, right? These are filters made of some media. Maybe it can be glass or quartz or something else. And then you store them in the laboratory for some time, because every day you have to collect one filter or maybe two filters. And then you try to do analysis for everything which is deposited on the filter. So you expose them to different kind of techniques like ion chromatography or atomic absorption spectroscopy, or even ICP, ion coupled plasma technique, to get an idea about what type of chemical species are present in this particulate matter. And once you have that information, you try to run a model, which is an invert model, to get what sources have contributed to it. So the idea is that some of these chemical species have some fingerprints of the sources which are present in the, actually in the atmosphere or in the vicinity where you have done this sampling. But as you see, currently as a part of Clean Air program, most of the cities are adopting this technique. But you can imagine that this process is slow, because you are collecting filters, you are bringing them, storing them, and then exposing them to analysis. And finally, you are running the model to get this information. It takes from somewhere 1.5 to 2.5 years before you get the result. Now, a country like India, which is undergoing a very rapid economic growth, certainly the overall scenarios related to sources are continuously changing. So to have a dynamic input into the policy making, this technique does not work. It can provide you a good baseline information, but dynamic input into the policy is not going to work. And therefore, we created a different way to understand source apportionment. We call it near or real-time source apportionment. where we deploy a couple of instruments, which are, for example, mass spectrometer or real-time metal monitors. Now, what you see in the second panel on the top cartoon, now from the snail pace, now we see a man is running. So from a 2 years time lag, you can bring down this duration to probably a week to 3 weeks. So you can get a real-time chemical speciation, and by inverting that information, you can get source information in near real time. That's one advantage. The second advantage is that what you see on the very right, there are those magenta or those violet color bars, which show that what are the sources which is contributing to these particulate matter, what you see. So there could be a whole range of sources. But the problem with the filter is that you cannot resolve them. So that's why you see some crosses. But in the second one, what you see, the real-time method gives you unprecedented information at molecular level. So you have a better ability to resolve sources with all its complexity, which is present in the in our cities, particularly in India. So that is what I'm going to basically walk you through very quickly some of the results we have. So 2 or 3 experiments we have conducted over Delhi NCR in recent years, which has covered right from Haryana, what you see on the India's map on top west north, from Hisar and right up to Kanpur, and currently we have also extended it to Lucknow. So basically we have covered a distance of about 1,500 kilometers over a year of 1 to 2 years, where these experiments were done in stages. And we have tried to get this information in near real time, and many a time this information has been shared with government, which they have found it even actionable related to the policy making. So this is a work which was done by my PhD student some time back. What you see in the center, you have map of Delhi NCR, and one station is right where Indian Council of Agriculture Research major presence is there near Pusa. So on the left, what you see, these 3 circles are basically these 3 pie charts, which shows what contributes to the major part of particulate matter, which we call organic. Okay, and that is what we are showing here. And of course, at the same time, other species which contribute to particulate matter is also shown here. So roughly speaking, what you see from these 3 locations over Delhi NCR, which is one at near Pusa, one at IIT Delhi, and third is a downstream site at Mano Rachna International University. Primarily, what you can understand that half of all the particulate matter is contributed by inorganic kind of species, and half of that is organic. And then you have those stacked bar for all the 3 pies, half of that, which is green in color. You also see that there are 3 distinct sources which contribute to the organic part of aerosols, which is oxygenated organic, which is aged organic. As I said, that as things travel in atmosphere, they get aged. Second is what you see, it is called that biomass burning related. And third is HOA, which is related to traffic. So the 50% of particulate matter is organic, and 50 of that is coming from the things which are formed in the atmosphere, and remaining 50, that is 1/4 of the total particulate matter, is primary in nature, which is coming from traffic and something related to the biogenic combustion or solid fuel, all that put together. Okay. Now, this slide actually shows a little result of little more advanced analysis. So here we wanted to understand that can we further dive deep into the understanding of sources to the organic aerosols. And what you see, the top pie shows the daily average values, and bottom is the daytime and nighttime, that we separate out that what contributes to that. And mainly our goal here was to understand what contributes to this secondary part of organic aerosols. which is more complex, that when you emit some of the gases or the aerosols, but then they actually undergo a very complex set of processes, physical and chemical, and then they finally give rise to these secondary organic aerosols. So it's very important to understand what sources are which are primarily contributing to it. And we could see that these are aromatic, lots of aromatic gases are contributing to it. There are some part of that is biogenic, which I showed in the very primer slide, that which is coming from the sources such as forest or trees, etc. Then you have an aged biomass, that the biomass which has been burnt elsewhere, and while traveling, it gives rise to what you sample here. And finally, you have also a mixed urban. This is a very complex something which is happening in the urban atmosphere. Okay. Then, as I said, that our goal also is to understand that how these particulate matter affect human health. So a very new technique, relatively new technique, which people have started employing is called understanding oxidative potential of particulate matter. This is called OP, and it is done by this chemical reaction, which is written inside the box. Basically, you do a chemical assay to estimate DTT. And once you have estimated, this is directly related to oxidative potential. Now, this gives you a mechanistic idea about how particulate matter actually are damaging the cells within your lung. So these particles goes into a lung, and there it deposits, and I said that then it flows into the bloodstream. So higher the oxidative potential, more harmful these particulates are. So here what we did, we measured it, and then it got published into a good journal, as you see, Environmental Science and Technology Letters. And we could also link it with distinct kind of sources, which are shown on the top, because we have the real-time information about oxidative potential, and we also have real-time information about different distinct sources which are contributing to it. Okay. Again, I think this slide is too complex to appear. So sorry about that. Something wrong has happened in slide transformation. This shows the results earlier were for summer, and this one shows for, results earlier were for winter, and this one shows for similar result for summer. One thing, what very interesting we found over Delhi by doing these measurements at IIT Delhi was to find an interesting source of particulate matter, which is cooking. Earlier, it was not so obvious from the previous studies. So here what you see that the time series of the sources are shown on the left-hand plot, which you see that traffic, coal combustion, cooking emission, less oxidized, and regional, right? And what you see that you are getting a very tightly stacked time series. So that means you are getting at a very high time frequency these results. And that is another advantage of such techniques. And on the right, you see is their diurnal variation, how these sources vary over a period of a day, right? So that is what you see on the right-hand side, those stacked plots. So if you look into the third plot, which is the light green color, and that shows a cooking organic aerosol, which has a very prominent peak around late evening. So these are, again, giving you some information that what all kind of things, economic or be it daily course related activities, which might be contributing to the emission of gases or particulate matter. And it gives you a good idea that what one could do about it, where one can work, where there are other cultural and other issues you cannot immediately work. So all these things will come out to the fore. This is another very interesting work was done by my PhD student, and again, very Delhi centric. We had measurements from two sites, one near Pusa, another near IIT Delhi. And we found that in the year of 2019, I'm sure most of you or some of you definitely follow the period which starts from early October to the December. And at least those who live in Delhi certainly experience very bad quality air and breathe it. 2019 stands out because from from middle of October to early November, we had a very bad, kind of worse episodes of couple of episodes of, polluted air we saw. And one of them we identified was related to this AGB here, which is agriculture biomass burning. So we saw that at that time, particulate matter would rise above 120, 130 microgram per meter cube on an average basis, which was done across few months, right? So we tried to understand why do we actually have given, attributed it to agriculture residue burning. So we tried to look into a couple of important markers here. And these markers are, as you see, are noted here, organics. And then you have BC is a black carbon. Black carbon is something which comes from particulate matter, or within particulate matter is primarily because incomplete combustion. If you do not do efficient combustion, black carbon comes in copious amount. And on the second panel, you have biomass burning organic aerosol. And then fourth one is little more aged, which is called little volatile organic aerosol. And finally, you have acetonitrile is a specific volatile organic compound, which is directly linked to the biomass burning incidences. Okay, it's well known that acetonitrile will come when you burn such kind of wood or bark or leaves, etc., or residue. And what we noticed here that at both sites, be it IIT Delhi or what we call, you have next to that is a MOES institute, and we call it IITM Delhi branch, which is just in neighborhood of Pusa. And you see all these markers definitely show an enhanced value compared to the rest of values. And that clearly shows that that episode in 2019 was driven by agriculture biomass burning. So that's a very interesting thing. You can understand that you can pinpoint it, and later on, if you can implement in models, then your models would have better ability to predict such episodes in future. Okay. This again was a work done over Delhi here, which is more related to understanding that what sources contribute to the metals in the particulate matter. Okay. Until now, we focused more on the non-refractory, non-metal part of particulate matter. But as you know, dust or what comes from power plant like ash or some other things have a huge contributions from refractory type of material, which we call like silica, etc. So here, what is shown is that what is the elemental composition of particulate matter over summertime in Delhi, which is the left pie. And you see it is majorly dominated by silicon and sulfur, because summertime you have dust, which is dominating expectedly. But the second most contribution comes from sulfur, because you also have a large demand during summertime of electricity, which is driven by the demand for air conditioning, etc. And then on the right, adopting a similar technique, we can also apportion that into sources. And that shows that, yes, that road or maybe transported dust is contributing to particulate matter primarily, and followed by power plant. And then there are some other sources as well. Okay. Currently, as I said, that we have shifted from Delhi. I just tried to show give some glimpses of the results we have had from Delhi. And now we have shifted from Delhi to Lucknow, which we can call as a central Gangetic Plain location. And we are now trying to understand again at a much deeper level. We are trying to separate out sources as far as possible. This is work going on in collaboration with Paul Scherrer Institute, Switzerland, where what we collect on filter, and then we try to expose it to, as you see, as the arrow is split out into two directions. So two very different, but very advanced kind of mass spectrometers. And what comes out, as you see, are at a molecular level mass by charge spectra you get. So in a low resolution spectra, you can get one kind of information. And when you try to resolve that, there are two time series shown here, two mass spectra shown, you can get a very detailed information, molecular information about sources. And that is what we have got it from Lucknow, which is the work done in collaboration actually with the Uttar Pradesh Pollution Control Board and even Department of Environment, Forest and Climate Change of Uttar Pradesh government, shows that during winter and summer, there are some very distinct kind of sources which are contributing to particulate matter in Lucknow, and sulfur containing compounds, which again, there is a large power plant close to Lucknow, depending on the wind direction meteorology, is also playing a major role. And interestingly, we have found that in Lucknow, the combustion sources are primarily or majorly responsible for high level of particulate matter compared to Delhi, and which also makes sense that except for agriculture biomass burning periods, Delhi generally would have lesser contribution from combustion related sources, because most of the Delhi, I think, has shifted to LPG, etc., for indoor cooking, right? Very briefly, I would also give you some idea about the source contributions to this non-methane volatile organic compound, because I mentioned that volatile organic compounds are important because they themselves can harm human, and while transforming into particulate matter, of course, they have many other adverse impacts. So this also was basically done by deploying a different kind of mass spectrometer. This is totally different from what generally used for understanding aerosol sources or particulate matter sources. We call this PTR-MS, proton transfer reaction mass spectrometry. So this gives you very highly resolved information about these volatile organic compounds. So I'm only showing here results for IIT Delhi and the downwind site, which is at Mano Rachna. And interestingly, what you see here, we have listed here traffic 1 and traffic 2. Okay. And this is a very interesting information that came out, that traffic 1 is more associated with light duty vehicles like car, vans, etc., etc. And traffic 2 is basically heavy duty vehicles, for example, car or trucks, lorries, etc., etc. And we saw that basically it also fits quite well with the with actual regulations which were in place at IIT Delhi and Mano Rachna. But you see, if you look at the diurnal variation of traffic 1 and traffic 2 at these two places, traffic 2 has a very flat kind of variation over Mano Rachna, because there was no ban or restrictions on plying of these heavy duty vehicles, trucks, etc. But over Delhi, over IIT Delhi, during daytime, as you know, winter time, there is generally a restrictions on plying of these heavy duty. They only are allowed to enter from 10 p.m. to 6 a.m. And that is why you see there's a big dip in traffic 2. That is the second dose time series on the left-hand side plot. Okay. And that is what we have contributed with a whole year of data over IIT Delhi. And we have tried to understand that how the seasonal contributions to VOCs are giving overall annual climatology in a sense of the VOCs over Delhi. Now, very quickly, I will now give you some idea about this, the emerging technologies where we can use or leverage these sensor-based techniques to scale the footprint of monitoring over India. So just to tell you an idea, number that in India, given its population and overall number of towns only, major towns, you require about 4,000 government monitors. And as of now, real-time government monitors are basically 300. So any given time, around 250 to 300 works. So you see the number, the quantum jump you require in order to meet the monitoring needs in the country by factor of 10 or maybe 15. And most of these technologies are imported and very expensive. So in a way, it's a cost prohibitive. If you add the monitoring space of rural India, then of course, the whole thing even go further. It will only exacerbate. So we have been working in this area for some time, for about 5-6 years, where we are trying to integrate these sensors in India, in the country, and try to understand, improve its accuracy, affordability, transmissibility, etc., etc. Okay. So one interesting work we did about 4 years back, which has found a lot of traction in abroad, and now also Indian agencies are recognizing it, where we try to understand the precision and accuracy of these sensors. Okay, because sensors cost you 1/60th of these government monitors. So give you an idea that particulate matter monitoring systems, the reference equivalent grade, the good ones, cost you about 20 lakhs, and it's imported. On the other hand, the sensor integrated units can cost you about somewhere from 60 to 70,000 rupees. So you can understand there is a cost difference of a factor of 30 to 40. In the cost of one monitor, you can buy 40 sensors. But accordingly, the sensors may degrade faster, their performance may decay. And in fact, unless you understand their accuracy very well and you apply right calibration to it, maybe you will not be able to get the right data. So that is what we have been working on for some time. Here, what we have shown some results from Kanpur. Basically, by comparing on the x-axis, you have government monitor data, and the y-axis, you have sensor data. And we have looked into hourly averages, 24-hour averages for the monsoon period when you have low amount of particulate matter, and for basically post-monsoon winter time when you have high particulate matter. And we found that there is a great agreement. If you look or collect the data carefully and maintain the sensors well, then you have an agreement with an R squared of 0.85 to 0.9. And if you correct for temperature and relative humidity, some of these meteorological, co-founders, variables, then you can increase the accuracy even further. Okay. So basically, we got these encouraging results. So we started also looking into the gas sensors, because I mentioned that in India, you monitor for air quality purposes, you monitor particulate matter and you monitor 4 to 5 kind of harmful gases, which are ozone, nitrogen oxides, sulfur oxides, and carbon monoxide. These are generally mandated to be monitored by Government of India wherever there's a government monitoring station. So we try to look into the accuracy of 2 particular gas sensors, which monitor or measure NOx, nitrogen oxides, and ozone. And that is what we have shown here again, is the error incurred in the ozone and NOx measurements by these sensors compared to the government monitors, which we call gas analyzer, by making use of or by exploiting some of the very advanced machine learning techniques here. And if you notice that in both plots, basically as you go from left to right, you slowly move from very simple model, which are linear model, to regression tree. And finally, we have moved to very data hungry, very expensive, complex machine learning models. For example, that is called K nearest neighbor, D metric learning. This is a very advanced model. And what you see that in these violin kind of plots in both blue and orange, you see the error has been dropped down to 8 to 10% for ozone and about 12 to 15% for NOx. So this shows that there is a very promising future for sensor-based monitoring of air quality in the country if you try to take them, install them carefully, and take all the due diligence in data analysis and make use of machine learning and artificial intelligence technique. Okay. So in fact, these results excited some of the government agencies. So Maharashtra Pollution Control Board took a lot of interest, and they facilitated us by giving their whole Mumbai's ambient air quality monitoring network, which was comprised of 15 government monitors. So across 15 sites over Mumbai, for 7 months, we deployed 40 sensors. So it's a relatively large experiment we did. And the results was, again, even more encouraging, where we found that the overall uptime of census data is commensurate with the government monitor. Okay, that's result 1. Second, the error could be brought down to 10% across 40 sensors, and which were working for 7 months, covering 2 or 3 distinct seasons over Mumbai, and for very distinct environments. Some places there are lots of traffic in Mumbai. Some places are impacted by sea salt because 3 part of the Mumbai is covered with sea. And some places are more impacted by industrial aerosols. And even there are differences at the level of pollution. So this was again a very, very promising and interesting results. So currently we are basically expanding this network. In fact, running now in Delhi, Lucknow, Jaipur, Mumbai, we did this experiment. Currently, we have a network running in Chennai and Kanyakumari, and we are halfway in deploying a network in the city of Guwahati. So slowly such network, which is supported by Ericsson, and they are working well, they're transmitting data, and places like Jaipur, we have Rajasthan Pollution Control Board working with us as a partner. This is another interesting application of such dense network, which probably could make you a little enthused or excited about it, that this is a dense network of sensors running in Lucknow. We have deployed about 70 sensors in Lucknow. So just to give you a perspective, that there are six government monitors in Lucknow, and we have actually covered that with 73. So the government monitors are very important because they are giving you accurate data, but they don't have that coverage that you require to understand the level, sources, and distribution of pollution, or contribution from local to other places, to the city of Lucknow, or for that matter, any other city. So this is what is the coverage of the sensors over Lucknow city as of now, is running very beautifully. And we have done some very rigorous statistical analysis by involving some of the professors of IIT Kanpur mathematics and statistics department. And we have worked out what are the places which are shown in pink spots, pink circles over city of Lucknow, greater city of Lucknow, which all the time have higher or larger values of PM 2.5 compared to other. And we call them hotspot. Many a times, I'm sure you read from newspapers that there's a lot of interest to understand in Delhi. For example, why Anand Bihar always shows high value. Their government monitors always show high value. There is a reason to understand it. First, you want to identify it. Second, then you want to do something about it. Then if you understand it, then you can do something about it. And that can prevent the adverse health impacts to the people who are living in the neighborhood of hotspot, or those who are traveling, whether it's a school going children's, or if there are hospitals, etc., etc. Okay. So, and then there are other applications also currently we are working on using sensors, because I showed a very advanced approach, which was real-time source apportionment, but that is very expensive, very cost intensive, and also resource intensive, because that requires a lot of manpower and trained manpower. So all the time you cannot actually work with that, you cannot scale it up. So what we are working now, we are using these sensors to train sensors with the real-time measured information and make use of AI, artificial intelligence, so the sensors start predicting sources. This is the next step currently we are working on, and that is what is shown here. Basically, if you look in the third row, where now a man is really a kind of sprinting ahead. So from snail pace to a jogging to a sprinting man, without having any loss of information, which is in the very right bars, what you see. So without loss of information, you are making use of sensors. All you need to do is to place sensors next to, or you rotate real-time source apportionment kind of infrastructure, and make use of that co-located data, make use of these some of the emerging machine learning and AI techniques, so that they start predicting sources. And we have some very interesting results already coming in, where we saw on the left pie is the actual information, the source information, source contribution to PM coming from the real-time source method. And on the right is the information you are getting from sensor-based data. And the results actually have a good match, and therefore it's looking quite promising. So I am almost now at the last stage of my presentation, very 1 or 2 slides. So Dr. Agarwal, how many minutes I have? Would you please just tell me?
No problem. You can just finish your talk.
Okay, so I'm almost done. Thank you very much. So here what I'm just showing that we had a nationwide capacity building program, which was supported by World Bank. We launched it in February and it ran through end of March, which has about altogether two major components to it. One was the induction training, and second was to create a framework for launching such programs in future, which is also linked with the national skill qualification framework. So that idea is that you train people who are employable, right? That people find the training commensurate to the job they are looking for. So about 400 people across academia, consulting firms, regulators, government agencies, and urban local body officials who attended this program, which were all actually imparted, delivered online from early February to end of March. And there are other also plans to take it forward. That is what it shows the overall reach of this program. And there is a final slide here, which I'm just showing now, is that we have just got some good support to create a rural air quality sensor-based network. And we are starting that with the states of Uttar Pradesh and Bihar, where we are covering around 1368 rural block, or what is also called these days are intermediate panchayats. So in Uttar Pradesh, there are 75 districts, and in Bihar, I think there are just little over 50 districts, and they both have respectively 850 plus 550 kind of these blocks. So the idea is that we'll have this rural air quality network running in these two states starting from next June. This project has already commenced and work is in progress. And by next June 2023, we should have these two states will be connected with this network of sensors covering the rural air quality, because there were some very impactful work. In fact, one came out in Proceedings of National Academy of Sciences 1.5 years back, work carried by an Indian scientist based out of US, which showed that rural air quality is fast deteriorating. So it's quite important that we understand it. We understand what is contributing to it. Is it the local sources like rural household cooking related sources, or it's because of the contribution from the urban areas, and it's more, so basically it's a more regional pollution, or it's more driven by the local sources. Okay, so yeah, I will stop it here, and I will be happy to take some questions. Again, I profusely thank ICAR, Indian Council of Agriculture Research, for giving me this opportunity, and thanks to Dr. Agrawal for taking all these efforts.
Thank you, Professor Tripathi, for giving from the basic to a very advanced idea, which is, I think, new to all of us, because the kind of research we have done in this field has been very educative for us. You have been involved at all levels, whether it's a research, policy, or in this listener ear network. So it has been a great learning, I think, for almost all of us. If you allow, we can take a few questions.
Yes, yes, of course.
Yeah. So the first question is by Dr. Rathore, who is working as national coordinator in NEHEP. Is there any technology which can avoid air pollution happening in Delhi because of the crop residue burning in nearby states? And how much is the oxidative potential of the pollutants of crop residue burning? And further, he is asking how Delhi becomes a gas chamber during winter season. The air quality deteriorates very badly.
Okay, so there are three questions. I think let me take them one by one. So generally, this is a practice to attack on source rather than trying to remove particles or gases from ambient. I always try to give an analogy that even in river, you don't clean by putting some chemical or something in river. You try to always plug what comes from municipal sewage or industries, etc. And just compare the overall volume of a large river like even Ganges and the volume of Gangetic plain. So I think there is a difference of probably 1 million or 10 million. So it's very difficult. You can always create some confined clean spaces, that is small space like colonies, and you can put something what is currently being talked about in Delhi, etc. But it is better to always act. So for agriculture residue burning, I think the solution is to, as I understand, is to create a consensus with all stakeholders so that we have a gradual in our complex political and societal setup. We need to gradually move to or shift, make some shift in our crop pattern. We also need to enable farmers and others so that slowly they totally shift from residue burning in the farm. And we need to have all those infrastructure in place soon so that the residue can be transported, stored, and can be harnessed, leveraged in whatever fashion. Either you want to create the brick pellets or you want to create, those what you call LPG or CNG or whatever, right? Now that is part one. The oxidative potential, the exact magnitude of that, I don't remember. But one thing I forgot, because that slide just next to my first primary slide on oxidative potential was a very detailed slide where we have actually from all 5 locations over Delhi, we could link oxidative potential, and by using 3 distinct kind of assays. So that was a really loss of a very nice slide, but doesn't matter. These 3 oxidative potential we could link to distinct sources. But the primary message from that, where we are just working to submit a paper, probably to a high profile journal, is that secondary organic aerosol actually are they disproportionately contribute to oxidative potential. So partly to answer your residue crop burning, that what comes close to what people breathe close to crop burning sources probably will not have so harmful effect, but as it travels, it becomes secondary. What we mean by secondary is that from primary, it transforms because of something happening in the atmosphere, because I said it's a reactor. So the secondary inhalation or inhalation of secondary particles will be more harmful. So that is answer to a second one. And the last one, you said that why it becomes gas chamber. I think there are 2 or 3 major factors which contribute. But if you have to pin down, I think there are 2 main factors. One is that the weather very clearly plays a role, because the atmospheric mixing literally stops from 3rd week of October to early December, because you have that lowest layer of the atmosphere simply collapses to 70-80 meters. So you have very little room for the pollutants to disperse or go out. And the fact that you have crop residue burning, other sources which are already operating, and as the winter sets in, then there are many other very unorganized sources. There will be more demand for wood burning because of the temperatures dropping, trash burning, and even probably some of the industries already are working. They are already spewing whatever they are spewing. So all put together actually makes it, as you mentioned, that kind of a gas chamber. So that is why the commission has come in place. I think they have just submitted a report. Let's hope that something comes out and something happens on that by this winter.
Thank you, sir. Dr. Anuradha is asking, is there any study on the role of urban forest patches like the Riz forest in Delhi in mitigating particulate matter air pollution, especially in terms of the type of tree species?
Actually, the trees or forest, as for climate change is concerned, is very important. We all know that there is no 2 ways that we need to have more forest in order to basically take carbon dioxide from atmosphere, and it also mitigates these urban heat islands. So forest needs to be there. Now forest is a double sword when air pollution comes. So you need to have carefully selected trees. So some people have, I think from Delhi University, have done some studies. That's because some forests, as I said, can contribute to this volatile organic compound, like terpene, etc., very well known. And in summertime, as the temperature rises, trees actually start emitting more of these VOCs, and which can contribute to the secondary organic aerosol formation. So I believe overall forests are a good thing for both mitigating or combating climate change and air pollution. But when it comes to air pollution, I think we just need to be careful about the choice of the trees we want to plant.
One last question we can take, that is from Sachinanandan. They are just complimenting you first for the presentation and the information which you have provided, and they are asking if there is any way to identify biological or pollutants, pathogenic bacteria adhering to dust particles play a major significant role. By adhering to the alveolar epithelium, it may cause an infection in the lungs directly.
Yes, I think biological particles are very important component of particulate matter. And there are techniques now, both offline and online. I think people try to collect them in a very specific way, and then they bring to laboratory, and then I think they give them agar, which I think most of their culture scientists should know, that food, and then they try to measure positive and negative bacteria, and then they go further and do the DNA analysis, etc. But there are also now techniques which can provide you these overall number or quantity of the pathogens, not necessarily pathogens, but maybe let's say bacteria which are associated with the dust particles. By, I think, looking at some efflorescence, there are some new techniques which actually look at, because some of these bacteria actually in a particular way interact with light and give signal. So I know that there are one or two techniques you can get directly, because you are right that getting the pathogens detected is important, because sometime, and many times we have seen during actually this COVID-induced COVID times, that is important for certainly for indoor pollution. It's quite important that we are able to detect these pathogens which are associated with particulate matter. So there are some other works people have been able to identify, even some using sensors also to identify some of these pathogens, very specific one, not all kind of pathogens.
Thank you, Dr. Tripathi. Dr. B.N. Tripathi, sir, you want to add something? Can you make him the co-host, please? Just a minute. Arpit, just make him the co-host. Allow him to speak.
Sure, sir.
B.N. Tripathi. Yeah. Could you do it? Yes. Now you can unmute.
Okay, thank you. Thank you for the opportunity. I think it has been a very comprehensive talk, right? That from air pollution to cleaning of air, how Government of India is concerned, and we knew that it is simply that if we not generate any like residual burning, etc., that make our air polluted. But it is a lot of science involved in that. That is how Dr. Tripathi has brought it. That how he has been doing. I think he has been doing for the last 25 years on this atmospheric science and aerosol. I've been listening to him for the last several years. That how he has been able to develop technology, low-cost technology, putting sensors across the country, different state, different centers.
Especially the Taj Mahal study.
Yeah, and it also. And once, I think maybe just 2 years back, there was a high polluted, in Delhi. Then he was asked to just go for the artificial rain also. He was heading that committee as well. That in Delhi, if it is required, Then IIT Kanpur, headed by Dr. Tripathi, he can create an artificial rain so that we can get rid of air pollution in Delhi. So he has been doing an excellent job for last several years, and we have seen that he has been trying to make us understand what is science behind aerosol formation, size of aerosol, and how it is dangerous for the health, even in the rural areas also. Not only concentrating on rural, but in rural areas also, and how government is concerned and running program to how to get clean air, in the country. So they're all working on a very national level. So I must congratulate Professor Tripathi for an excellent talk involving a lot of science. Though I was attending other meeting also, but the way he has presented right in the beginning, that there are different areas he has touched upon, and how other institutions are working with the development of technology, low-cost technology, and ultimately with the objective to India to have a clean air, and because we are the one, we are the highest polluted country in China and India. So that's a great work. And one thing I was just wondering that is there any microbiologists from your IIT, they're also involved with your work. Somebody asked a question that how this aerosol maybe conducive for a pathogen to be aligned with that, and it can go along with the aerosol, it can go to the animals or humans and affecting causing many diseases. So I think it will be a wonderful idea that along with your work, you also collaborate with a microbiologist, so that he can also look for the possibility if there's any predisposition of dangerous pathogen due to this polluted air. Apart from the polluted air itself is harmful for humans and animals. But is there any microbes like any virus and bacteria that become more get more conducive environment in the polluted air and infect humans and animals and that become health hazards? So that part I would like you to also look into that. So
Dr. Tripathi sir, is there any study on the effect of this air pollution on the animals?
No, it is very difficult, for that you have to create an experimental model. That is very difficult, that we have to, polluted air should be, it should be taken in some jar, and then you have to expose animals mostly for a few hours, and they'll see the effect. I think I'm not aware of such a study. But certainly laboratory model, IIT can do it, because IIT currently they have got biotechnology department also. So there are a lot of very good biotechnologists and microbiologists also there. So I'd like to have his reaction on this, if he can, tell something.
Good. So thank you very much for nicely summarizing this talk. So Professor Tiwari, I'm on behalf of Indian Council of Agricultural Research. We are really thank you very much from the bottom of our heart for giving such a nice information, giving the details of your research work, giving the details of the government initiatives for controlling this air pollution, which has become, I think, one of the most severe problem, at least in the metropolitan cities. I know it is there in the small cities also now. A lot of pollution you can see, but in metropolitan cities, it's really very difficult. And the kind of activities, initiatives you are involved in, I think it's praiseworthy. And we are really proud of your research, your initiatives, your contributions for the very noble cause. So thank you very much once again for sparing the time and for providing all these insights into this important topic. So, and I thank all the audience, the eminent audience from our universities, from ICAR, and the students especially for attending this important talk. So thank you once again.
Thank you. Thank you, Dr. Agrawal. Thank you.
Okay, bye. डॉक्टर गवाह आपने मीटिंग तो अटेंड नहीं किया?